are forces whose total work done is 0, and then the conservative force, F conservative of xy, it can be written as negative the gradient of a potential energy, and then this has units of joules. So F conservative is negative partial u partial x I hat, negative partial u partial z k partial z partial y j hat. And then that potential energy is the energy that you can store in that force. And then the work done by a conservative force, right, which is equals to integral of the force times dr, that's equal to negative the change in potential energy, negative delta U. So negative U final minus U initial, which is U initial minus U final. Okay, so then that's what they're going to talk about in this website. Theorem, fundamental theorem of line integrals. Suppose a curve C is given by the vector function R of t, where A equals R of A, B equals R of B, then the delta F dotted into dr, which is really this thing, right? This is the gradient of this, dotted into dr. So in my case, I'm calling this delta U, right? So the symbols you use is not what matters, but it's the concept that matters. And that is equal to U of B minus U of A, provided that R is sufficiently nice. I guess whatever that means, right? Proof, and then they do the formal proof of that. Okay. Then they go into if a vector field F is the gradient of a function, F is delta F, we say that F is a conservative vector field. Oh yeah, so in their case, the little f that they're using is the same as what I'm calling U, with potential energy. And then a big F is the force vector. So F is a conservative vector field. If F is a conservative force field, then the integral for work is in the form required by the fundamental theorem of line integrals. This means that in a conservative force field, the amount of work required to move an object from point A to point B depends only on those points and not on the path taken between them. You see, only the initial point and the final point. So, example 16.3.2, an object moves in the force field, this force field, negative y, negative z, along the curve r is equal to 1 plus t, t cubed, and this. So it's a three-dimensional path, right? As t ranges from 0 to 1. Find the work done by the force on the object. So if we wanted to find the work done by that force, how would we do it? Well, if we don't use the fundamental theorem of line integrals, we would just do F conservative, well, work for any force is just going to be Fx dx, Fy dy, and then Fz dz, right? So it's going to be integral, so Fx is going to be negative x over x squared plus y squared plus z squared to the 3/2. So this is f, the x component of f, right? Dotted into the x component of the path that it's taking, right? Which is going to be dx from let's see. Okay, so x, if t ranges from 0 to 1, then what is the range of the x? Because in other words, this is the x of t, right? X of t is 1 plus t. Y of t is equal to what? T cubed. Z of t is going to be t cosine pi t, right? And then t goes from 0 to 1. So what is the range of the x, right? So if t goes from 0 to 1, the initial x is what? 1, and then 1, that's 2. So then that's the the work done in the x direction, right? F of x dx plus f of y dy and then what y goes from 0 to 1, right? So y, what are the limits of the y? 0 to 1, right? And then f of z dz, right? And then if you put 0 here, what do you get? 0, okay, you just get 0. And if you put 1 cosine of pi, what is that? Negative 1, right? And that would be the work done. That would be one way to get the work done by that force, right? So it says, the straightforward way to do this involves substituting the components of r into f, forming the dot product of f r prime, which is what we did, right? And then trying to compute the integral. But this integral is extraordinarily messy, perhaps impossible to compute. Is that pretty hard?
You can do U sub.
Huh?
You could do U sub.
Yeah, they're saying it's kind of hard. But they're trying to basically use this as an example to say, well, if you don't want to do that integral, then you check to see if the force is a conservative force, and there might be an easier way to do it for conservative forces. Perhaps possibly compute. But since f equals the gradient of this, in other words, can we test to see if this force is conservative, right? So if f is conservative, it can be shown to be the gradient of some function, or the negative the gradient of some function, right? And is it? They're saying it is. It's the gradient of this function. Force is the gradient. So this is the potential energy function, right? Of which that force is the force field. So this is its associated potential energy function. U of x, y, z. This is actually three-dimensional, right? So what function is there who this is the gradient of? So then you say 1 over x squared plus, how did they get that? Did they just guess it? 1 over square root of x squared plus y squared plus z squared. Was that just a pure guess, or is there a methodology of getting that? In other words, you have to find a function whose derivative is the force. That's given, right? How do you do that? Okay, here's what you have to do. You have to say function. You have to find a function whose derivative in the x direction is this guy, whose derivative in the y direction is this guy, and then whose derivative with respect to z is this guy. So partial u, partial x needs to equal what? This one. Partial u, partial y needs to equal this one. And then partial u, partial z needs to equal this one. This one was easy to do because it's a pretty easy function, you know. So now, if we do that, then what other way is there to find so then we prove that this force is conservative. In other words, it can be the derivative of some function, right? So then, if it is conservative, how else can we find the work of that force? Then we can just say minus the change in potential energy of that function associated with that force. Okay? So then we can say the work of the conservative force is minus the change in potential energy. In other words, minus potential final minus potential initial, which is potential initial minus potential final. Right? So then, what am I doing? I'm getting the potential energy and taking its initial value at the initial x, y, and z, and then minus the final. So 1 over square root of, what was my initial x? I think my initial x is 1, right? My initial y is 0, right? My initial z is also 0. Minus 1 over square root of, then my final x is what? 2 plus my final y is 1, and my final z is negative 1, right? So that's going to be 1 minus what? 1 over square root of 4 plus 1 plus 1, 6. That's going to be the work done by the force, the change in potential energy of the function. In other words, the path that it took doesn't matter for us in this case. You see? So I think that's the answer. Did they get that? 1 over root 6.
Oh, it's opposites.
Let me look this up. Work is equal to
1
minus potential energy minus delta U.
I feel like it should be delta U, right?
No, it should be negative delta U. Right? If something drops, how much work does gravity do? Positive, right?
Right.
So is that equal to potential final minus potential initial, or potential initial minus potential final? It should be potential initial minus potential final. Potential initial is higher. So potential initial minus potential final. I think they did it wrong here. It should be this one. That should be the opposite. Yeah, write to them, say, hey, we found a mistake. It should be potential initial minus potential final. They did potential final minus potential initial. So another immediate consequence of the fundamental theorem of both closed paths, and then a closed path, we already talked about that last week, is 0, right? The work done in a closed path is 0. Okay. Example 16.3.3. Find an f so that this function is equal to the gradient of f. So in other words, they're giving you the force again, right? And they want you to find its associated potential energy. They're calling f, the little f is the potential energy. So that one is like example 1. This is like example 2. We say the potential energy, I prefer calling it U because we're giving it physical meaning. So U is equal to, sorry. This is the force that they're giving you, force. So that's equal to 3 plus 2xy I hat plus x squared minus 3y squared j hat. Right, newtons. So how do we even know that this is a conservative force? How do we know that it has the properties of a conservative force? Well, properties of a conservative force, it has to have an associated potential energy function. The work done has to be path independent. The total work done in a closed path is 0, right? The best way to do that is to show that this means that f of x, to show that the derivative of this with respect to, if you take the derivative of f f of x with respect to y, right, is going to be what? Keeping, in other words, keeping x constant, right?
I thought they were integrating.
Huh?
I thought they were integrating.
No, what they're saying is, first, note that. In other words, how do they even know that the force is conservative? They take the derivative of this first part, the x component of f, with respect to y. And then they get what? They hold, in other words, they hold x a constant, treat x as a constant, taking the derivative with respect to y. And then you get 2x. Okay? And then the derivative of the y component with respect to x. Now they hold this constant, the y constant, so the derivative of this is 0, and the derivative of this is 2x. Right? That means they're equal. And so now the force is conservative. Okay? If the force is conservative, then what is its associated potential energy? So now we want to find the potential energy f of xy is equal to negative partial u partial x I hat minus partial u partial y j hat. So in other words, we want a function whose derivative in the x with respect to x is equal to this guy. So minus partial u partial x is equal to 3 plus 2xy.
Why is it negative?
Well, because of the directionality. If the gravity does positive work, then the potential energy, we're losing potential energy. It's just a matter of preference. So then we have here negative du is equal to 3 plus 2xy dx, and then integrate. So u of xy, u of x is going to be what? This is the derivative. This is going to give you the so integrate this with respect to x while keeping y constant, right? So then it's going to give you what? 3x plus x squared y.
So that's the constant.
Plus some constant. Because potential energy always has some constant added to it, which is the reference point. Then u of y is going to be what? The integral of this guy. U of xy, right? So minus partial u partial y is equal to x squared minus 3y squared. Should I have distributed the negative on the other side? In other words, should this be negative 3x, negative x squared y? Or could I keep the negative on the left side? I think it depends on what the constant is. Probably it doesn't matter. Then integrate this, negative du. Integrate, let's see, u of xy, integral of this with respect to y, x squared y minus y cubed. Then combine these two, right? Because what? Potential energy is a scalar, not a vector. In other words, this isn't the x component of u, and this is the y component of u. It's all one function, right? So we can combine this guy plus that guy, okay? Let's see what do they do.
So you just write out what the respectable variable or constants are.
This means that f of x is 3 plus 2xy, so that f is 3x plus x squared y. Is that what they did? 3x plus x squared y, right? Plus g of y. The first two terms are needed to get 3 plus 2xy, and the g of y could be any function of y. Oh, that means they're saying this constant here can be any function of y because its derivative with respect to x is going to be 0, right? So instead of s constant, they're putting g of y here, right? G of y. And then they're saying, likewise, since f of y is x squared minus 3y squared, f is equal to x squared y minus y cubed plus h of x. So x squared y minus x cubed plus h of x. Right? Then what's going to happen? The question now becomes, is it possible to find g of y and h of x so that 3x plus x squared y plus g of y is x squared y minus y cubed plus h of x? In other words, we're going to set these two functions equal to each other. And of course the answer is yes. I see what happens. In other words, this is some function here of x. Because if I take the derivative of this with respect to y, this is going to be 0, and then I'm going to get this guy. Right? And if I take the derivative of this guy with respect to x, I'm going to get this guy. Right? So then these two functions should be equal. You see that? So then I have here x squared y minus y cubed plus h of x is equal to what? Potential energy x of y, which is where's the other one? U of x y, 3x plus x squared y plus h of y, or g of y. So what function of h of x is there that I can put there, and what function g of y is there? Let's see here.
You cancel out the x squared y, no, and then you spell out what a function.
Yeah, you see the x squared y matches x squared y. And then what should g of y be?
The other function. That's
Yeah, okay, yeah, there you go. This one cancels this one. Have you guys done this in Calc 3?
Yeah.
Yeah? And then therefore, g of y must be this guy, and h of x must be this guy, right? H of x is 3x, g of y is negative y cubed, okay? And therefore, what's going to happen? Where's the eraser? Therefore, the potential energy function, whose negative gradient is this, is given by that function. U of xy is equal to x squared y minus y cubed plus h of x would be this guy, 3x. Right? The negative gradient of this gives you this. So we've gone backwards to find the potential energy. What does that mean? How would we interpret this? Now in Calc 3 you might not go one further step to give this meaning. But in physics we do. We say, what does this mean? Well, this means joules, right? So this could describe the potential energy that a particle has in a two-dimensional field. So imagine the ground right now, right? So imagine the middle of the classroom is x is 1, 0, y is 0. What would the potential energy be at that point? U of 0, 0. That would be 0, right? If this was the potential energy function. So if we had a ground that was kind of like this, you know, kind of elevated and had all of this thing. So if this represented the height of the ground, that would be the potential energy that the particle would have at that point, right? So it'd be 0 joules, so that'd be the reference point. So then what's the potential energy at 1, 1? 1 minus 1 plus 3, that'd be 3 joules. So if I put the particle at the 0.11 meters, so if xy was there, 0, 1, 1 would be somewhere here, right? It would have potential energy 3. So would it want to go downwards? Yeah, objects always like to go towards lower potential energies. That means it will roll down that path, right? And every single point in space would have the elevation to it, which would be equivalent to saying what its potential energy is, right? You -1, -1. That would be -1 squared, -1 minus -1 cubed plus 3 times -1. What would that be? 1, -1 minus -1 cubed is -1, -3. That would cancel. -3 joules. Oh, that means -1, 1 has even a lower energy than 0, 0, right? So how do we find the point that has the least potential energy? You have to maximize and minimize that potential energy function, right? The point that has the minimum potential energy would be what's called a saddle point, right? In 2 dimensions.
Well, you gotta do the second derivative test.
Yeah, second derivative test, right? Yeah, exactly. Yeah. Let's see. You see? So basically what we're describing is like some kind of a function. You can do good computer-generated images like this, right? Every function, x and y can be a plane. The vertical z can represent the potential energy of the particle, right? And then objects like to prefer points of low energy, you know? Points of highest energy are unstable equilibrium. They teeter. If you displace it, they go towards lower energy. You see? So points of relative max, we call it, relative maximum of potential energy yields unstable equilibrium. Lower points, stable equilibrium, because if you displace, it goes like that. You see? So that's what you learn in Calc 3, finding those points. See, these are all local maxima. That's unstable equilibrium. And then local minima would be these guys. Local maximum, local minima. What was a saddle point called? Was saddle point neither local minimum or maximum?
Yeah.
Saddle point. So would that be a would that be stable or unstable? Saddle point.
I think
It's probably unstable in one direction because it's like this and like this, right? So if you displace it like this, it'll go back and forth. But if you displace it like this, it goes down, right? So depending on which way you displace, it could be unstable or stable saddle points. Like this. The reason they call that is because a saddle that you put on a horse is like that. You see? It goes like this, and then it goes like this. See? Okay, so the one we're gonna do more specifically, because in order to do a 2-dimensional one, you need to know a little bit more specific Calc 3 skills, doing Lagrange multipliers and stuff. So we're gonna focus on 1 dimension. So scale it down now. You guys can do the finding the potential energy now, but I'm not gonna ask you now find its saddle points and maximum and minimums. That requires more skill. But how about 1 dimension? Well, 1 dimension, you should be able to find it. Okay, so in this case, it's a one-dimensional force, right? 3x squared plus 6x plus 8 minus 8. So what is its associated potential energy function and the points of stable and unstable equilibrium? Then you're given a scenario. If a 2 kilogram object starts at x equals 0 meters with initial speed of 2 meters per second to the right, what happens to that object, right? So to find the associated potential energy, what do? We say F is equal to negative du dx, right? I hat. Therefore, negative du dx needs to equal 3x squared plus 6x minus 8. So then just take the integral of that. U of x is going to equal what? So we can take the negative over there, negative 3x squared minus 6x plus 8, then integrate it. Negative x cubed minus 3x squared plus 8x plus a constant. But since they don't tell us anything, then we just can set the constant equal to 0. So joules. In other words, negative derivative of this, if you did it right, if you take negative derivative of that, you should get the force again, right? Negative the derivative, you're gonna get that, the derivative of this, you're gonna get that, and negative the derivative of this, you're gonna get that, right? Okay, so how do I find the stable points of equilibrium? Or unstable? Well, then you find all the critical points of this, which is equivalent to saying go back to the force and set it equal to 0, because force is the derivative of that, right? Set that equal to 0. Okay, so put that in solver. Tell me what you get. Answer.
I have negative 2.915 and positive 0.915.
Negative
915
and positive
0.915.
0.915. Oh, same?
Yeah.
Oh, okay. Okay, now how do I know which one of those yields stable equilibrium and which one yields unstable? So to visualize it, it's best to think of the graph of the potential energy function, right? U of x. So how do I graph the potential energy function? So now think about the graph of this. What is it gonna look like? When x equals 0, it's gonna start out as 0. So at the point 0.915, is it going to have a local max or local min? Right? Well, then we can take the second derivative of u, do the second derivative test, right? When you're doing this, remember that when you take the derivative of this, it's going to give you a negative of that, right? So u prime is going to be negative of that guy. And when you take the second derivative, then it's going to give you negative 6x minus 6, right? In other words, negative of that, then the derivative of this will be negative, and then the derivative of this will be 6x minus 6. So now when you put 0.915 in here, if this comes out negative, then that means it's concave down, it's a max, right? So 0.915, what is that? It looks like it's negative, right? Some negative number. Okay, so that means that is max. So at 0.915, some maximum potential energy max. So the function probably looks like this. When x goes to infinity, what happens? The limit of this as x goes to infinity is negative infinity, right? So that means it goes like this. And then as you go to negative infinity, then it's infinity, right? So then it's like this, like that, right? So all your stuff that you've learned in Calc 1 now comes into play. Graphing techniques and stuff, right? So now we need to find, the other one is going to be local min, right? Which is the 0.295. So something like this. Okay, so now that gives us an intriguing thing. So you can almost think of like a railroad track. And depending on where the particle is initially placed and how much of a kick you give it. So according to part B, a 2 kilogram object is placed at the origin, but you initially give it a speed of what? 2 meters per second, right? Now if you left it that way, what would it, if you didn't give it any kick, you left it like that, it would just oscillate until it reaches zero again, right? The energy reaches zero, because it starts out at zero, so it would oscillate and come back and come forth, right, like that. We're assuming there's no friction in this space, right? So, but since you're giving it a kick, it might actually go and may have enough energy to go over, right? Or it might go up, stop, then come back, and then oscillate forever, like that, you know? So how do we know how much energy we gave it? It depends on that, right? How much kinetic energy did we give this? 1.5 times 2, its mass is 2 kilogram, and its velocity is 2, right? We gave it 4 joules of energy. Right? We gave it 4 joules of energy. So then what's going to happen? It's going to go 4 joules, but then what is the maximum here? U min. Okay, so it's going to go, but I want to know what the maximum potential energy is here. So then I need to take the 0.915 and put it into the potential energy function, right? Find out what U of 0.915 is. So then take 0.915, negative 0.915 cubed, minus 3 times 0.915 squared, plus 8 times 0.915. So do that, let's see how much potential energy.
4.040.
Oh, that is close. 4.042. Wow. They call that potential energy in chemistry what? The energy required to get a reaction going, right? What do they call that?
Catalyst.
Huh?
Oh, sorry.
Activation.
And activation energy, right? Activation energy, right? So in other words, if you start here, reactance, we want to get over there. So we have to go over a hump to get to that state. This is the final state. This is the reactance. So you need to go through a transition. So it might be that you mix some sugar in the coffee and you need activation energy for it to saturate. So you just mix it. Your spoon gives the activation energy, you know? Or maybe you don't have a spoon and you don't want to put your finger in it. So you go, oh my God, what do I do? You put it in the microwave, you heat it, then you swirl it. That gives it enough activation energy, you know? Or you heat it and then you put your finger in it. Well, it's really hot. No, just kidding. Yeah, so there's all kinds of stuff. So what we're doing is kind of applying this not necessarily to chemical reactions, but to any kind of motion of an object. It's got a hump to go over. It prefers to be in the lowest energy state. But then if we give it a kick, it might go over, you know? So in our case, the 4 joules of energy we gave it is not enough. So it's gonna go all the way to stop somewhere here, stop, then come back, go really fast when it reaches here, then go all the way until its energy is 4 joules again, and then go and come back. So to make your answer complete now, find out what point, which 2 points it oscillates around, and what is its maximum velocity at the bottom. Okay? That makes your answer complete. So how far does it go before it stops? And how far does it go on the other side before it stops? How do you find that? Set the potential energy function equal to 4 joules, exactly. It's all visual. You gotta visualize what you're doing. You gave it 4 joules of energy, set the potential energy equal to 4. Right, so the potential energy is negative 3x cubed, negative what? Integral of this? X cubed, right? Negative 3x squared plus 8x, right? Set this equal to 4, right? That's potential energy. And you're probably gonna get 3 answers, here, here, and here, right? But then you give these 2 answers, right? So you say it oscillates between the points x equals to something and something. So one of your answers is going to be like almost 0.915, right? Point 9. Oh, it's that much different? 0.8 to 8?
Negative 4.82.
Okay, negative 4.82. So it oscillates between these 2 points and reaches maximum speed at x equals to the point where it was potential energy min. Reaches maximum speed at x equals to negative 2.915. The maximum speed, V max, is equal to what? So how do you find the maximum speed that it reaches there? Okay, well, the initial energy, the initial potential energy it had was 0. The initial kinetic energy you gave it was 4, right? So initial kinetic plus initial potential must equal to final potential plus final kinetic. So the initial potential was 0. You gave it 4 joules of kinetic energy. What's the final potential? So then you take the negative 0.2915, put it back into that function, find the potential energy that it has here, right? So find that out. What's the minimum energy here? Oh, that deep. So it's almost like this. Negative 24. Wow. So then you're going to have potential energy initial is 0, kinetic is 0, negative 24.042 plus the kinetic energy, half times 2 times V final squared. 2 cancel, 24 goes over there, and then this is 4. So negative 24 goes over there, that becomes 24 plus 4, 28.042 is V final squared. Then equals square root of that. So that the final velocity we'll have here is the maximum velocity. So it goes like this, speeds up, slows down to 0, then speeds up, speeds up, speeds up, like that. See? So that's going to be 5 point something, huh? Square root of 28.
5.295.
Cool, huh? Now what if we had given it a tad bit more velocity? Let's say we had given it an initial velocity of 3 meters per second. What would your answer be to be complete? Yeah, it would be a completely different scenario, right? How much kinetic energy would you have given it? Now the kinetic energy initial is 1/2 times 2 times 3 squared, 9 joules. So now you have 9 joules of energy. So now it goes up, 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 up. It slows down, and then has enough energy to go over. So your answer will be, it goes to the right until it reaches its slowest speed at the point x is 0.915. Then it keeps going, and then its speed keeps increasing till infinity, you know, and it could go almost at the speed of light by the end, you know, because it's just gonna go this way, okay, and its speed is gonna increase. So your answer is it goes to the right, reaches the slowest speed at x is 0.915, and then keeps going. Its slowest speed is equal to, then you would give me what the slowest speed is. So how would you find that? So now you're not giving the maximum speed, you're giving the slowest speed, right? So it goes to the right. The answer would be, it goes to the right until it reaches slowest speed at x equals 0.915, and then keeps going and speed keeps increasing. V min is equal to, then you would tell me what that slowest speed is. So how would you find that? Then you said it's initial kinetic plus initial potential equal to final kinetic, final potential again, right? Initial potential is 0, initial kinetic 9, final potential is what? 4.042, right? That it has at that point. 4.042. Then you subtract them and you take the square root. So 2 point something, right? Are you guys getting it? Ask questions. Mark, you ask questions. You look like you're a little bit.
I don't even know what questions to ask. You lost me a long time ago.
You don't remember this stuff from calculus? Local max, local min?
It's been a while. I have to refresh myself before I get to the next question.
Oh, there's a lost tool completely. Okay, well, since you're lost, we go now to the next chapter. Right? When people are lost, that means you just keep moving. No, it's supposed to be the other way around, but unfortunately, we don't really have the time, right? Okay, we gotta go to chapter 9, impulse, momentum, center of mass, collisions. Ooh. Good stuff. So a good time to, I guess, stop the video and then restart it.